Let's start with the lecture. To recap what we were doing last time, we kind of defined this new object called the adjoint of a linear transformation, which we saw is basically a fancy version of the transpose of a matrix if the matrix has real entries, and the conjugate transpose of a matrix, which is also called the adjoint of a matrix, if the matrix has complex entries. And this is kind of an extension of that for the general linear transformations. So we don't quite define it in terms of entries of anything, but rather in terms of how it behaves. And the way it behaves is that it kind of gives us the right conversion to do sort of to map inner products in the W space to inner products in the V space. So if you have an inner product in the W space, you can write down the inner product of W and phi of V, because V maps V to W, and it sort of gives you the right mapping so that you can compute the inner product in the V space, and phi star will map W to the V space so that you can compute inner products there. Okay, and yeah, we sort of saw a couple of examples. I also, I mean, maybe the matrix example and also some sort of example in the vector space of functions. And I assigned an exercise about the Fibonacci space, as always. And we also saw that the adjoint always exists and is unique, at least if we are working with finite dimensional inner product spaces. Okay. Something like this is also true in Hilbert spaces, but then you need to know something additional about this transformation phi, that it satisfies some sort of continuity property. But again, we won't need that fact in the course. Just if you want to look it up, it's the same proof can be made to work in Hilbert spaces with slight assumptions on the transformation. Okay. Any questions about any of this before we proceed?
Really quickly, could you maybe clarify for me what the P star is in relationship to phi?
What phi star is? It's, I mean, phi star is another linear transformation which kind of maps in the reverse direction. It's something which depends on phi, but we can't always, I mean, or we sort of saw how to write it down using this kind of Rees representation theorem and so on. It's not something which I can immediately kind of, I mean, abstractly say for a phi, but if you're thinking of phi as a matrix, then we kind of saw what this is. So if you have, let's say, a matrix A, which is, let's say, m rows and n columns. So you can also think of A as a linear transformation mapping the column space to, or the space with the current dimension based on the number of columns to space with the dimension number of rows. And we saw that here the condition we need is that for all V, which is in the space we are starting from, W in the space we are going to, the inner product, and if you consider the kind of standard inner product or the usual inner product on Rn and Rm, then what we wanted that if let's call it A star to be the adjoint of A, and the property we wanted is that the inner product of two vectors which are in the W space should correspond to the inner product of two vectors which are in the V space now. And we sort of saw that we can take A star to be just A transpose. I mean, if you look through the proof of what we did in the Rees representation theorem, this is sort of what happens for a generic linear transformation in a finite dimensional inner product space also. It's just that you sort of, when you write out the matrix in the usual way, you're kind of writing it out in the basis of the vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, or the kind of standard basis vectors, which have one coordinate 1 and the other 0. Which do form an orthonormal basis under the standard inner product. And for a general linear transformation, it is essentially this. It is sort of the transpose of some matrix you can obtain, but you have to write down the transformation as acting in the right kind of orthonormal basis under the inner product you are given, and so on. So it's a little cleaner to kind of write it down not as a matrix, but just as a linear transformation. But yeah, if you want to think of it as conjugate transpose or transpose, it is really that. Just when you are working in the V space with the orthonormal basis for the inner product under V, and in the W space for an orthonormal basis, the inner product under W. Does that make sense?
Yeah, I think that helps. Thank you.
Okay, yeah, and yeah, I'm happy to discuss more after the lecture if you want to go over the definition again, etc. Yeah. All right, so that's so maybe a quick recap of things from last time, which is the adjoint. Again, it's just, yeah, you can think of it as generalizing some properties of the transpose or conjugate transpose, which, I mean, the important property we are sort of interested in is what it does to inner products. And this is a way of generalizing this to abstract linear transformations and abstract inner products without really knowing exactly what the inner product is, exactly what the transformation is doing. We can still say that such a thing always exists and is unique, at least in finite dimensional spaces. Okay, and then we kind of started talking about a special kind of linear transformations, or really operators, which are mapping the same space to itself. So these are linear transformations, linear operators. Sometimes the word linear is kind of omitted, especially when you're talking about operators. Yeah, I'm certainly talking about linear things. And we call a transformation from V to itself self-adjoint if, well, it's equal to its own adjoint. So what does it mean? It's equal to its own adjoint. Whatever properties we were asking for phi star, which is that the inner product of W and phi of V is equal to inner product of phi star of V and W. I mean, in the usual definition, the object that plugs in here is phi star. But we are saying that we can plug in phi itself. And because, again, if you're working with a finite dimensional space, the adjoint is unique. So if phi works, then that's the adjoint. I mean, there is nothing else to find. Okay. And just a quick check. So for matrices, we kind of understand what the adjoint is. And now, if you are thinking of a matrix as a linear transformation from a vector space to itself, then it's a square matrix. Sort of the number of rows and number of columns is equal. And now, a quick sanity check. What does it mean that the matrix is self-adjoint, it's equal to its own adjoint? So we just saw on the previous slide how to define or what is the adjoint of a real matrix, a matrix with real entries. What is the adjoint?
Quick question.
Yeah.
Quick question.
Yeah.
So if you write the self-adjoint definition as this W comma phi v equals phi of v comma W, this only means that, I mean, this kind of means that the inner product entries have been switched, meaning that, the conjugate inner products are defined.
Oh, sorry. Yeah, you're right. My bad.
It should be phi of
yeah.
W comma
No,
v.
you're right. Thank you. And the object we would have plugged in here is,
right.
Yeah, I mean, phi and phi star are applied on different vectors when we sort of write this inner product condition. And here, instead of phi star, we can use phi, but yes, they are still applied on different vectors. Thank you. Okay, sorry about that. Now let's go back to the question I was asking. What can you say about the matrix A if we want to say the matrix is self-adjoint? Can you interpret it in some other way? Going back, what is the adjoint of the matrix? Matrix A? We just, okay, sorry?
It's symmetric, asymmetric.
Right, so the adjoint of matrix with real entries is A transpose, and here we are just saying that the matrix is self-adjoint, means that A transpose is equal to A, right? Because A transpose is always an adjoint for any matrix with real entries and under the usual inner products. Adjoint is unique, and we are saying A also works as an adjoint, so they have to be equal. And this is what we know as symmetric matrices. Okay, what about complex? Again, you can think of the usual or the standard inner product on C to the n. You can think of a square matrix mapping vectors in C to the n to C to the n. And I'm claiming that it's self-adjoint.
I guess A equals A star, Hermitian.
Right, so A star, or what we call the conjugate transpose of the matrix, serves as an adjoint for complex spaces. And now we are saying A serves as its own adjoint, so these two have to be equal. And such matrices are called Hermitian matrices. That's just a name in case you see it in literature anyway. These both kind of matrices are nice. They have some sort of extra nice properties compared to other matrices in terms of eigenvalues, eigenvectors, etc. And these are kind of common in many applications. For example, if you think of a graph as a matrix, then its adjacency matrix, at least if it's an undirected graph, is always a symmetric matrix, and a lot of these nice properties apply to it. And this is a basis for what is called kind of spectral graph theory, etc. Okay, any questions about this? Okay, so let me develop on this point that self-adjoint matrices or Hermitian matrices or symmetric matrices are nice, and in general, actually, self-adjoint transformations are nice. So recall that when we are working with, so few things are kind of hidden under the hood here. When I say phi is mapping V to V and is self-adjoint, to even have adjoints, we must have inner product. So when I say this, V must be an inner product space. Otherwise, definition of adjoint doesn't make sense, right? I mean, in general, when it's mapping V to W, both V and W must be inner product spaces. And when I say something is an inner product space, I mean, it's a vector space, and then there is some inner product defined on it. So I'm kind of, to specify an inner product space, I have to tell you what the vector space is, what the addition, scalar multiplication notions, etc. are, what the field is, and what is the inner product. And we said that we'll only work with fields which are complex numbers or real numbers. So we'll still stick to that. And so in general, when you have a linear transformation, it can, first of all, it may or may not have eigenvalues. If it has eigenvalues, they can be field elements, which in this case can be real or complex numbers. But for self-adjoint transformations, yeah, we'll see more about this. But if you have an eigenvalue, it is going to be a real eigenvalue. And in fact, you will have eigenvalues, etc., which we'll get to in a bit. But and kind of a slightly upgraded version of what we saw for generic transformations, that if you have eigenvectors corresponding to distinct eigenvalues, then they're orthogonal. Okay. So their inner products are 0. And if you remember, kind of, so basically in inner product spaces, we get to kind of upgrade a lot of our statements about linear independence to stronger statements about orthogonality. So when we said a vector space, we always have a basis. When we talked about inner product spaces, we have an orthonormal basis. So it's stronger than just linear independence. For linear transformations, we got to say that when you have eigenvectors corresponding to distinct eigenvalues for generic linear transformations, they are linearly independent. Here, we get to say that at least if you have inner product spaces and self-adjoint linear transformations, which are even more special, then the eigenvectors corresponding to distinct eigenvalues are not just independent, they're orthogonal. So we get these kind of stronger properties than just independence. Okay. Any questions about the statement before we proceed to the proof? So let's start with the proof of the first property. Okay, and it's really sort of an exercise in kind of just applying the definitions of adjointness and inner product. So all eigenvalues we want to prove real. So let's say let lambda be an eigenvalue. In general, lambda can be an element of the field or a complex number if the field is complexes. If the field is reals, then there is nothing to say. And let V be an eigenvector. So let's say we have phi of V is equal to lambda times V. And V is a non-zero vector. Okay. And now we'll sort of use the only thing we know about self-adjointness. So we will say when we have the inner product of W and phi of V, we can write it as the inner product of phi of W and V. But now we'll apply this to the same vector V, which we know is an eigenvector. So let's also take W to be equal to V. And now it is indeed as if we have kind of switched the order of things in the inner product and still obtained the same value. But now let's see what this inner product is. Okay, so because V is an eigenvector, we get that this is phi of V is equal to lambda times V. And now, because the inner product is linear in its second input, we get lambda times the inner product of V with itself. And because it's conjugate linear or antilinear in its first input, we get that this is equal to lambda conjugate times the inner product of V with itself. So these two things are equal. Now, V is non-zero, so the inner product of V with itself is a positive real number. We can cancel it on both sides. And we get that lambda is equal to lambda conjugate. A complex number is equal to its own conjugate if and only if it's a real number, right? So if you have a complex number that is equal to its own conjugate, then it's a real number. Okay, any questions about this? It's just sort of following the definitions of self-adjointness. Okay. Now let's prove the second part of it. It's sort of similar proof that you kind of apply the definition of self-adjointness. But now we want to prove the orthogonality of eigenvectors corresponding to distinct eigenvalues. So let's say we start with Wi and Wj with I not equals to j. So they correspond, they're eigenvectors corresponding to distinct eigenvalues. And now let's see what happens when we apply the definition of self-adjointness. So self-adjointness tells us inner product of Wi with phi of Wj is equal to the inner product of phi of Wi with Wj. And now I get the inner product of Wi with lambda j times Wj, and this is equal to the inner product of lambda I times Wi with Wj. Again, using linearity, I can write it as lambda j times Wi inner product Wj, and I can write it as lambda I, really lambda I conjugate, but I just proved that lambda I is a real number, so I don't need to worry about conjugation. And these two must be equal. Or lambda I minus lambda j times Wi inner product Wj is equal to 0. Since lambda I and lambda j are distinct, the only way this can happen is when inner product of Wi and Wj is 0. So this we know is not equal to 0. So then this must be 0. Okay, any questions? Right, so that's, I mean, a couple of nice properties we get with self-adjoint transformations that, I mean, and then we'll see more, but the eigenvalues are real and the eigenvectors corresponding to at least distinct eigenvalues are orthogonal. It's not necessarily the case that eigenvalues are distinct. I mean, you can look at the identity matrix or the identity transformation where the phi of v is just v. And you can find an orthonormal basis, or you can find many different eigenvectors, all corresponding to eigenvalues 1, right? In fact, every vector is an eigenvector with eigenvalue 1, every non-zero vector. So it's not true that when you are working with orthogonal vectors, the corresponding eigenvalues are necessarily distinct. It's just that if they are distinct, the corresponding eigenvectors are orthogonal. Okay. Now, this can be used to actually develop what is called the real spectral theorem. Again, my bad joke, but it's not that other spectral theorems are fake. This is about just real eigenvalues, and spectral, this kind of self-adjoint operators have real eigenvalues, and hence the name. Okay. And I mean, these kind of theorems can be proved for a somewhat more general class, but we'll restrict ourselves to this kind of self-adjoint operators or self-adjoint linear transformations. Okay. So it's kind of going one step further from what we said earlier. Earlier we said, if you have an eigenvalue, then it's a real eigenvalue. And if you have two different eigenvalues, then the corresponding eigenvectors are orthogonal. Now we are saying the if can be basically removed. You will have many eigenvectors. Each eigenvector will have an eigenvalue. And in fact, you can find an orthonormal basis of eigenvectors. So you can find enough eigenvectors to essentially, to basically span the space, and they will form an orthonormal basis, which is kind of very convenient to work with under inner product. So it's a really nice basis, and we'll see that this is a very nice basis to think about in terms of this transformation. Again, going back to matrices, this will kind of mean that in a different basis, we can write this matrix as essentially a diagonal matrix. And this will kind of make it convenient to work with. Going back to what I was saying about graphs, etc., it's quite important to find this orthonormal basis of eigenvectors. And in some sense, they carry a lot of information about the transformation. If the transformation is, let's say, the adjacency matrix of a graph, then these eigenvectors carry a lot of information about the graph. And these are used, for example, in what are called spectral partitioning algorithm, where you want to kind of divide the graph or some object into two pieces with certain properties of how the pieces interact, etc. This sort of right kind of basis for what are called noise operators, etc., is also what you use in Fourier analysis in different settings. So finding the right orthonormal basis for the kind of operators you are interested in, if they're self-adjoint, can be very, very helpful. In fact, these basically tell us a lot of information about the operator. Okay. And the real spectral theorem kind of tells us that it always exists. And in fact, it sort of gives us a recipe for computing it. But let's start with something simple. So let's start with this matrix. It's a symmetric matrix, so it's self-adjoint under the usual inner product on R2. And I can observe that this matrix has two eigenvectors. I'm not telling you yet how to compute them. I just kind of created this matrix so that I know the answer anyway. But just for illustration, let's see that it gives us these two eigenvectors. Okay, and the eigenvectors 1 and -1 are orthogonal under the usual inner product on R2. And if I really want, I can make them orthonormal just by scaling the vectors. So I can look at these vectors, which are 1 over root 2 times 1, 1, and 1 over root 2 times minus 1, 1, minus 1. These have norm 1 or length 1 under the usual inner product on R2. And they are still orthogonal. So this is an orthonormal basis for R2. I just need 2 linearly independent vectors. Orthogonal vectors are linearly independent, so they form a basis. But these are both eigenvectors, and as we'll see, this has some very nice consequences. Any questions?
Does it still have an orthonormal basis if I change the inner product definition?
Yes, well, as long as the matrix is still self-adjoint under that definition. So whether something is self-adjoint or not depends on the inner product. Right? So as long as the inner product is something where it is self-adjoint, yes, it still has an orthonormal basis, which is orthonormal also under your new inner product. If it breaks self-adjointness, then I'm not making any claims. Okay. All right, good. Yeah. Please stop me if something is unclear. Right? All right, good. So now let's prove this theorem, and we'll spend maybe a fair amount of time in the lecture proving this theorem. We'll prove this in 2 steps. One, and we'll show that this kind of the if part of what we were saying, if it has an eigenvalue, and we wanted to say that we can remove this if. So we will show that it has at least one eigenvalue. Okay, so and then we will kind of use induction. So we will use induction to essentially shave off this eigenvalue. Think of this operator as on a space with 1 less dimension, and then show that it has at least one eigenvalue on this space. And then think of a space with 1 less dimension and show that it has at least one eigenvalue on that space. And keep doing this. And while we are doing this process, we will be sort of finding eigenvectors via induction. Okay. So let's first kind of assume step 1 that a self-adjoint linear transformation has at least one eigenvalue, and use it to show that we can find an orthonormal basis. And then we'll come back to this issue of finding one eigenvalue. Okay, is the plan okay? I mean, yeah, we'll implement it, but we're going to assume that it has at least one eigenvalue, and then we'll try to prove this theorem. I'm just writing the theorem again, maybe in a slight shorthand. Okay, so because there is at least one eigenvalue, there is an associated eigenvector, because an eigenvalue kind of the definition of eigenvalue requires a non-zero v such that phi of v is equal to lambda times, right? So where lambda is an eigenvalue. Which we assumed exists. Okay, there is at least one eigenvalue, and because of what we know about self-adjoint transformations, lambda is a real number. It can be 0, just that v is not 0. And now I claim that we can basically pass to a different space. So, so let me clarify what I'm doing. We're doing an induction on the dimension of the space V. Okay, so and this is just the first line is just how we interpret the assumption. Okay, so now let's start with the base case. So now we're starting with a space with one dimension. We know there exists at least one V such that phi of V is equal to lambda V, and we want to find an orthonormal basis of eigenvectors. Okay. So we just need to know that this vector V is non-zero. Right. Because it doesn't need to be orthogonal to anything. There is only one dimension. So we just need one non-zero vector to span the entire space. One vector is linearly independent. And all we need is that it should have norm 1, and that we can just ensure by kind of dividing it by its norm, so that when you take the inner product, it just cancels it. Okay. Any questions about this part? This is what we did also in the base case of Gram-Schmidt. We have one linearly independent vector. We can convert it into an orthonormal sort of orthonormal set, which for one vector is not really super difficult. Okay. So now let's say the dimension of V is k plus 1, and let's say we've already proved this theorem for, or let's say the dimension of V is n. And let's say we can assume this statement for n minus 1 dimensional spaces. Okay. So again, let me call this eigenvector okay, that's fine. So we have, there is some eigenvector now. Let's define this space W, or rather, actually, maybe I should call this eigenvector W, just so that I'm using consistent notation for the space. And let's define the space of vectors which are just orthogonal to this W. Okay, is the definition of this W perp clear? It's just a space of vectors which are orthogonal to W. Notice that this only makes sense in an inner product space, and we couldn't have defined it in a general vector space, but now we have, and then this is also a space that appears in the homework, I think. So maybe you already saw this kind of space. And I think one of the problems in homework is to show that such a space is a subspace. The dimension of W perp, I claim, I mean, we'll see these statements if we need proof. The dimension of W perp is n minus 1. And for every vector U which lives in W perp, phi of U also lives in W perp. So So you can also think of phi as a linear transformation mapping this space to itself. Because when you start with a vector u, which is in W perp, the image doesn't go outside. So phi can also be thought of as a linear transformation. And the fact that it's linear follows from the fact that it's linear in the vector space V in this space W perp. And then we'll apply induction to sort of say that because of this, we can use our inductive hypothesis. Any questions? I mean, we'll argue about these 3 points I wrote down, but any questions about the plan, assuming this? Okay, so let's just first kind of again take these properties of W perp and then finish the proof with that. So now we have phi, which maps W perp to W perp, and W perp is an n-1 dimensional subspace. Okay, and actually we need more. To use our inductive hypothesis, we also need that we have a self-adjoint operator, not just any operator. So we will also need to show that acting on this space, phi is still self-adjoint. But okay, let's say we have all that. Now we can say by induction, there exist vectors, let's say W1 to Wn-1, which are an orthonormal basis for W perp and are eigenvectors of phi. Again, if you've seen the matrix proof of this, is it sort of by kind of arranging entries so that you can change the matrix to a block diagonal form, etc. This is just the generic version in a product spaces for this. In fact, yeah, this proof is a bit cleaner because you don't have to write those sort of slightly more complicated matrix transformations. So by induction, this space W perp, there is an orthonormal basis of eigenvectors for phi because this is an n-1 dimensional space, and by induction we can say that here the real spectral theorem is already true. Okay, and if that is the case, then we can say now take the union. So now look at the set W1 to Wn-1 and add this new vector W, maybe normalized to length 1. These are all eigenvectors because W was an eigenvector to begin with. That's how we started the induction. W was some vector which was an eigenvector of phi. And then we look at the space W perp, which was the space of orthogonal vectors. So W is an eigenvector. W1 to Wn-1 are eigenvectors. And W1 to Wn-1 are an orthonormal basis. So in particular, they're all orthogonal to each other. And they're all orthogonal to W because they live in this space W perp, which is the space of things orthogonal to W. Right? So, so we get that these are all eigenvectors of phi, and they form an orthonormal set. And there are n of them, and the space is n-dimensional, so they should be enough to span the space. So we have a basis. Yeah, that's kind of assuming the behavior of phi on this space W perp, or that's kind of completing the induction. Now let's think about how phi, so it's already in the homework, and I'll let you argue that this space is a subspace, and also that the dimension of W perp is n minus 1. I mean, quickly, the dimension of W perp is n minus 1 because we have an inner product space. We can always have an orthonormal basis. Or in fact, we can complete any set to an orthonormal basis. So start with the set with this little vector W, complete it to an orthonormal basis, and the n minus 1 things you added to get an orthonormal basis are a basis for the space W perp. So there is at least one basis with size n minus 1, and hence the dimension. Okay. Now we want to say that phi acts on this space and maps it to the space itself and is self-adjoint. So the first thing is to prove that the image stays within this set. And for that, we need to say that if you start with a vector v in W perp, that is the inner product of v with this vector W was equal to 0, then you still stay in this space, and after you apply the transformation phi, or the inner product of phi with this is still equal to 0. And this is because, well, using self-adjointness, which we haven't used so far, by the way, we can write it. We can move the inner operator to the other side. Oh, sorry, again made the same mistake. We can move it to W. W is an eigenvector, so we get the inner product of V with lambda times W. And we have a linear transformation, so we get lambda times V inner product W. And this we already said was equal to 0. So the image of phi also stays in the same space W perp, but it doesn't go outside. And moreover, I claim that it's self-adjoint. So if you have the inner product of W1 and W2 in this space, then they are still in the space V. And phi is self-adjoint in the space V, which means you can move it to the other vector for any two vectors in the space V. So in particular for the space W perp. So this is just following the definition of self-adjointness again. So for any two vectors in the space V, I can do this. So in particular for two vectors in the space W perp, I can do this. Okay. Any questions about this part? So I claim that this kind of completes the induction, or at least if we assume that there is one eigenvalue, then it tells us how to find an orthonormal basis of eigenvectors, because if you have an n-dimensional space, there is one eigenvalue. You kind of you sort of think of the eigenvector W and this space W perp, which is of one less dimension. The transformation on this space maps to itself, or this maps the space to itself and is still self-adjoint. So by induction, you can find an orthonormal basis for this space and then put back the eigenvector you started with. Any questions? feel free to ask me to revisit something if something is unclear. Okay. Otherwise, I'll proceed to the next part of the proof. Okay. To prove that there exists at least one eigenvalue, we'll need to use some algebra. And again, there are a couple of different sort of proofs of this fact. Again, for matrices, sometimes you talk about determinants, etc. Here we're talking of general linear transformations. So we'll use a proof which is a bit different, but in fact, there is kind of this fun book called Linear Algebra Done Right, which tries to do linear algebra without using determinant ever, because it's trying to do it for general vector spaces. And there's also a counter book called Linear Algebra Done Wrong, if you want to look at it. But yeah, it's kind of fun books to look at. Here, we'll use sort of a theorem from algebra, or just about polynomials, is that if you have any polynomial, let's say over with complex coefficients, then it has at least one root. So it has there is some kind of complex number alpha such that P of alpha is equal to 0. Okay, this is called the fundamental theorem of algebra. You might have seen it in undergrad, but yeah, it's just that any polynomial has a root over complex numbers. Okay. And this is sort of like there exists an eigenvalue, and we'll use this to prove it. But again, kind of iterating this statement, you can prove that if it has one root, then you can actually find many roots. In fact, you can factorize the polynomial. So if a polynomial has one root, then this can be written as a factor, because again, when you do kind of polynomial division, divide by P of x by x minus alpha, the remainder, I mean, in general, you will have a remainder, which will be a degree 0 polynomial, because you divided by a degree 1 polynomial. But when you plug in alpha, a degree 0 polynomial is just a constant, by the way. And when you plug in alpha, this has to be 0, but so the only way a constant is 0 is if it's just always 0, right? It doesn't really depend on alpha. It's a degree 0 polynomial. So you can write, so x minus alpha must be a factor. And then you can apply the same theorem to q, which is some polynomial. So it has at least one root. This root is a factor of q of x, and you can pull it out. So you can repeat this and write p of x as a product of factors. In particular, if you had degree n, then you will have n factors. And just comparing coefficients for x to the n, if you write the factors this way, then it should all be multiplied by c to the n, the cn, which is the coefficient of x to the n, just for the two expressions to be equal. Okay, so another way fundamental theorem of algebra is stated is that a polynomial in complex numbers can always be factored into linear factors. Okay. Any questions? So this is a theorem we will use. I'm just sort of reminding you roughly how it's proved, or roughly how how to go from existence of a root to factorization. I'm assuming existence of a root. Okay. And this can be used to prove the fact that there is at least one eigenvalue, at least when you're talking of vector spaces over complex numbers. Okay. You have to do a little more work to talk about vector spaces over real numbers, and inner product spaces we could talk about either. But because the theorem is about roots under complex numbers, we can prove this for operators over on vector spaces over complex numbers. Okay. And there actually we don't really need self-adjointness. So this theorem is true in more generality. And we will still prove that it has at least one eigenvalue. And for self-adjoint operators, we can really do induction. So we can actually get many eigenvalues, which is the interesting part. Any questions about the statement? And here we'll really just apply the statement about polynomials that we just saw. So let's say we start with any non-zero vector. And then let's consider so it's a finite dimensional space. So let the dimension be n. So I'll use n to write the space. And start with any vector and then write down the following vectors: phi of v, phi square of v, phi cube of v, and so on, all the way up to phi to the n of v. And this sort of notation again appears in the homework. So phi square of v is just a shorthand for phi of v. This is just a shorthand for phi applied 3 times, and so on. Right? But these are some vectors, right? You start with v, apply phi to it, you get some other vector because it maps vectors to vectors. You apply phi again to this vector, you get some third vector because it phi maps vectors to vectors. And so you get n plus 1 vectors in V. And if you remember one of the first examples of linear dependence in R2, one of the examples given was that any 3 vectors are linearly dependent. Similarly, if you have an n-dimensional space, then any n plus 1 vectors are linearly dependent. So they must be linearly dependent because we have too many of them. We can't have n plus 1 linearly independent vectors. So because they are linearly dependent, there exist coefficients C0 to Cn such that Cn times, let's say, phi to the n of v plus Cn minus 1 times phi to the n minus 1 of v all the way to C0 times v is the 0 vector. Right? Because these are just n vectors, and I'm just multiplying them with coefficients. These are just n plus 1 vectors, and they can't all be linearly independent. And now we just go back to our polynomial. So we want to think of what we are doing here as kind of applying a polynomial in the operator phi to the vector v. So formally speaking, we just say consider the polynomial, which is sort of the same coefficients as above, but now just in some variable x. Okay, so this is some polynomial. We know we can always write it as a product of some factors, and let's call these factors, instead of x minus alpha 1 to x minus alpha n, let's suggestively call them x minus lambda 1 to x minus lambda n. These are just my names for roots of the polynomial. Okay. Any questions about this so far? Yeah, I just said there is some linear combination which is 0, and I just used that linear combination to define a polynomial. And now let me
quick question here.
yeah.
So if you write it as a polynomial, then you have this dependence between terms that x. Yeah, I guess I'm a little confused how you can write this as a polynomial.
Okay, so I'm not necessarily yet saying that I'm writing this as in the expression that I'm looking at as a polynomial. I'm just saying I'm considering a formal polynomial, just a polynomial with some variable, abstract variable x, a formal variable x, and the same coefficients. So I'm just copying the coefficients right now and just defining a formal polynomial. But you can also think of writing the expression as a polynomial. So let's consider as an example. Maybe that clarifies things. So let's consider the kind of expression which is phi square of v minus, let's say, 3 times phi of v plus 2 times phi. Okay. So here I've just plugged in some concrete values for C2, C1, and C0. Okay. N is equal to 2 in this example. And if I just consider the polynomial p of x, which is x square minus 3x plus 2, I can write it as a product of factors x minus 2 times x minus 1. And using this knowledge, I can also say that, and that's what I'll say next, but yeah, it's a good point to illustrate that I can say, if I think of phi minus 2 times the identity operator applied to phi minus the identity operator applied to v, then I get back the above expression. So what does it mean that I consider phi minus the identity operator? Well, I start with v and map v to phi of v minus v. And then I call this, let's say, w. And then I map w to phi of w minus 2w. Okay. So overall, this is some mapping of v. I start with v, and first I map phi of v to v. And then whatever this vector is, this w, I map it to phi of w minus 2 times w. So it's some complicated thing on v. And I claim that what this is doing is mapping v to this whatever expression was on the left, because we can check that phi of w minus 2w is equal to phi of, remember, w was defined as phi of v minus v minus 2 times phi of v minus v. And now you use linearity to say that the phi of v minus v is equal to phi square v minus phi of v. So you can use linearity to say that this is equal to phi square v minus phi of v plus 2 times, or sorry, minus 2 times phi of v minus v. And that's exactly what we had here, which is phi square of v minus 3 times phi of v plus 2. So you can think of applying this polynomial in terms of its factors to V and obtaining the expression which we have, which is a linear combination of phi to the n times V, or phi to the n acting on V and phi to the n minus 1 acting on V, and so on. Does that make sense?
Yeah.
Okay, so good. So that actually helps me make. So now let's sort of define. So okay, let's just recall what we had. And by what we said in the previous example, we can also get that Cn times if we apply these transformations one by one to V, this is the same as computing this polynomial that we just wrote down. Which, by the way, we know is equal to 0. So now let's see what happens after we kind of apply these factors one by one, or after we do one of these things. So let's define W0. So this is just kind of the same proof as we were talking about. I mean, again, you can prove this by induction on n if you want to, just follow the previous proof. And in particular, we define W0 to be V, W1 to be phi of W0 minus lambda 1 times W0, and more generally Wi plus 1 to be phi of Wi minus lambda I plus 1 times Wi. Okay. Okay. So we started with V. We mapped it to W1, then we mapped it to W2, and so on, and we mapped it to Wn finally. This was not 0, and this was 0. So we have this kind of chain of points we got. We started with V, we kind of applied some linear transformation to it, got something else, then we kept doing this. At some point, we must have sort of encountered 0. I mean, that might be the last one, right? So maybe the first time we saw 0 was when we computed Wn starting with Wn minus 1, or maybe Wn minus 1 was 0. I don't know, right? So there was some point when we had a non-zero vector here and a 0 vector here, right? This point might be Wn itself, because we started with non-zero. The leftmost thing was non-zero, the rightmost thing is 0. So at some point we will hit something with a non-zero on the left and 0 on the right. Once we hit 0, it will stay 0, because all these are linear transformations. They map 0 to 0. Okay, so now let's go back to the first point, such that Wi is not equal to 0, and Wi plus 1 is equal to 0. So left thing is non-zero, and the definition of Wi plus 1 is phi of Wi. Let me write it here. So this phi of wi minus lambda I plus 1 is equal to 0, which means that wi is equal to lambda I plus 1 times wi. And now this is kind of what we want. This is a non-zero vector. And the action of phi on this is just scaling, so this is an eigenvalue. So the first time this happens in this chain, we start with a non-zero vector, we get a zero vector, and that must be an eigenvalue. Any questions? Note that we didn't use the fact that phi is self-adjoint. In fact, we didn't even use the fact that V is an inner product space. We just use linear dependence that you have n plus 1 vectors in an n-dimensional space, then they must be linearly dependent. Okay. Now we need to kind of prove this over complex numbers. The kind of matrix proof, if you have seen, is that the eigenvalues are roots of the determinant, and the determinant is a polynomial, so it must have at least one root and hence one eigenvalue. Again, I don't necessarily need to want to define determinants. It's kind of tricky to try and do this for generic linear transformations, etc. So this is a proof which doesn't really need that notion. Existence of eigenvalues over real numbers, we can basically cheat. So if you have, again, go and think about, let's say, matrices. So if you had a matrix with mapping real vector spaces to real vector spaces. So let's say you have a matrix with real entries and it's self-adjoint. We want to prove that it has an eigenvalue. We can think of the same matrix as mapping complex numbers to complex numbers, right? Matrix with real entries still maps complex number vectors with complex entries. It still multiplies them by some real things. Those are still valid complex numbers. So basically, you can think of a transformation over real spaces to as a transformation over complex spaces. And here we will need to use self-adjointness to say that when we get an eigenvalue at the end of the day, it will be a real eigenvalue because, well, this complex action was just something we cheated and created. The vector space V was over real, so we should find real eigenvalues. So we will just kind of conceptually think of it as acting on the space V prime, which is just kind of the space of, you can think of it as formal sums of two vectors from V, where you can sort of, we can think of V prime as a space over complex numbers by just saying that you define the multiplication with complex scalars as if using the multiplication with real scalars that you have available in the space V. And this is a vector space over complex numbers. In fact, it's an inner product space, and you can show that. And we define phi prime, which maps V prime to V prime as phi prime of U plus IV equals phi of U plus I times phi of V. And okay, so I'll let you complete this proof as an exercise, but phi prime has at least one eigenvalue. So you'll need to show that this is self-adjoint. Actually, we don't really need that, but yeah, it has. Okay, we don't quite need that. But if you have an eigenvalue of this, and this is defined as phi of u plus lambda times, oh, sorry, plus I times phi of v, then you must have lambda as an eigenvalue of phi also. So you just kind of, this is just a formal operation. You just starting with an operator or linear transformation over real vector spaces, you can just define a linear transformation over complex vector spaces, find an eigenvalue for that, and just say that it must be an eigenvalue for the original transformation also. Okay, so it just, but to do this properly, now you need self-adjointness. Okay. Yeah, I sort of sketched the proof. I didn't give the full proof here. This I'll let you complete as an exercise. But do ask me if something isn't clear, or if you want me to go into more detail. All right. I guess we'll stop here and we'll not go into the next concept since, yeah. Okay. But any questions about the discussion? Anything you'd like me to clarify?
Yeah, hello.
Yeah.
Yeah, I have a question regarding the real spectral theorem. So when we defined the vector space W per, we so in the theorem statement we said that the linear transformation phi would be from V to V, but here we see that phi would be from W perp to W perp. So how do we conclude that?
Right. So I mean, it's just maybe I should have used a different notation, but here what I'm saying is that the theorem is that any linear transformation which is self-adjoint from a space V to itself is orthogonally diagonalizable or has an orthonormal basis of eigenvectors. By induction, we are assuming this for spaces of n-1 dimension. And here, what I'm saying is that phi kind of defines a linear transformation, let's call it phi perp, which maps W perp to W perp, which is just phi restricted to W perp. So for any element of W perp, just compute phi on it. Okay, so I just use the same notation, but formally it's a different linear transformation because it's mapping a different space W perp to W perp. But what does this do? It does whatever phi did. We saw this is true because phi sort of takes vectors in W perp to the same space. It doesn't map them outside and is still self-adjoint. So this phi perp is kind of formally a different transformation, but it does exactly what phi did. But now it's a transformation which, because phi maps things from W perp to itself, this transformation is from W perp to itself, which is an n-1 dimensional space. So we have an orthonormal basis for eigenvectors of phi perp. But because phi does exactly what phi perp does exactly what phi did, eigenvector of phi perp is also an eigenvector of phi because phi perp is just phi with a different name.
No, my question, so like, I don't know if it might be trivial, but like, how do we simply say that phi will take an element in W perp to W, like the image will also be in W perp? Like...
No, it's not trivial. We need to prove that. And in fact, I argue that what we have here is the proof. So we said, suppose we have any V which is in W perp. So we start with a vector in W perp. Then we want to claim that the image is also in W perp. So phi will take a vector in W perp and the image will be in W perp. We need to prove that.
Yeah.
To prove that, we check that Well, what we need to prove is that the inner product of phi of v with w is equal to 0. This is sufficient and necessary to say that phi of v is in w perp, right? Because the definition of w perp is things orthogonal to w. And we said by self-adjointness, this is equal to v inner product phi of w. By the fact that w is an eigenvector, this is equal to v inner product lambda times w. And by linearity, we can pull w out, and this is equal to inner product of v and w, which was 0. So we actually proved that this is 0. It's not obvious at all. We need to prove this. Okay. Once we prove that this is 0, now we got that phi actually maps w perp to itself. And so you can think of the restriction of phi to w perp as a transformation from w perp to w perp.
Okay. Yeah, that was it. Thank you.
It needs proof. Yeah, I should have been more clear. Any other questions?